Hello, everyone. Great to see a full house today for this very special event of the ICTS on the frontiers of science, which is what ICTS is about. It's a particular pleasure for me to introduce to all of you Professor David Gross, one of the giants of theoretical physics. You've all, and this is for the benefit of the non-physicists, but even for the non-physicists, you may have all heard of the Standard Model or the theory of particle physics, one of the most successful theories of nature that we have, describing to very high accuracy almost all phenomena that we see, excepting those of gravity. So it unifies all the other fundamental, it kind of brings together all the other fundamental forces other than gravity. And this happened in about 50 years ago. And I think it's a great fortune in one's life to play a role in piecing this understanding together. And that is what David has done. David played a central role in this in multiple ways, but especially through our understanding of the strong nuclear force, what is now called quantum chromodynamics, or QCD, as it's now called. And in particular, his seminal discovery about 50 years ago of the remarkable feature of the strong interactions, or QCD, of what is called asymptotic freedom, that unlike everything, any other force, fundamental force that we know of, the quarks are almost free when they come very close to each other, very different from how, say, two electrons or two masses behave when they come close together, right? And I'm sure you'll hear more of that. And this was a very revolutionary and very important, played an important role in kind of completing our picture of the Standard Model by bringing in the theory of the strong interactions, putting it on a similar footing to that of the weak interactions and electromagnetism. And it is for this seminal contribution that he received the Nobel Prize in 2004. But he has made other very landmark contributions to our understanding of Standard Model and QCD. So it was not just for asymptotic freedom that David is well known for. He was involved in the development of string theory as a theory of quantum gravity and much else, which I won't go into the technical aspects of, but we may hear some of it in this talk. But not only that, David has been a remarkable mentor to both people and institutions. For people, it's a interesting factoid for many of you, maybe, that he's the only person not only to win a Nobel Prize for himself, but had one of his PhD students, Frank Wilczek, also getting a Nobel Prize. But not just that, another student of his, so he's probably the only person whose students have gotten a Nobel Prize and a Fields Medal, the highest award in mathematics, and this is Edward Witten. As a former PhD student of his, you can imagine how tough the benchmarks were to be working with David, but it was always a privilege. And so that was people, and many things I could say there too. But as a mentor to institutions worldwide, he's also very unique, because I have not seen anyone who's given so selflessly, so generously time and effort around the world, not just in the United States, to many, many institutions around the world to create and sustain places of scientific excellence, because I think he would like to see the world populated with centers of science to kind of create a vibrant scientific culture of humanity. And for that, he has been really tireless in his advocacy, in his own personal time and energy. And we have been fortunate here at ICTS to have him associated with us from the outset over 20 years ago, first with Spencer and then with me, chairing our International Advisory Board, and therefore also giving me the opportunity to have him as my guru for the second time around, so to say. So that is again something I deeply treasure. Anyway, I will not go into all the long list of honors that traditionally is sort of recited at these occasions, because you can all now open up your Wikipedia page and see it. But I just want to mention something that a few weeks ago, he received this newly established Basic Lifetime Achievement Award of the International Congress of Basic Sciences. And I think that's a very fitting thing. It's a recognition of the tremendous contributions of David to science. But as David said on that occasion, giving a lifetime award kind of feels as if you've done your life's work, and David is not going to accept that. David still marches ahead. Anyway, so I present to you what I call the fifth force of nature, David Gross.
It's really great to be back here in this room, which I've been many times. Actually, this isn't the room I usually speak at, right? It is? Okay. Anyway, it's certainly great to be back here in India and Bangalore, and especially at the ICTS among friends. And this audience, which is, I gather, very varied, a lot of young people, some of whom might go into physics. My talk is aimed truly at them. So it's entitled The Frontiers of Fundamental Physics. And I'm going to talk about the frontiers of basic science, not the frontiers of technology, applied science, which start at well-established basic science, but rather frontiers of basic science that lead eventually to established science, to technology, and hopefully benefit society. So we have learned an amazing amount about the natural world in the last 50 years. Really quite remarkable. For example, we've learned and understood in our field of elementary particle physics, standard model that Rajesh referred to, we've discovered and understood the basic building blocks of matter, what we're all made out of, and the forces that act on them. The same period, we have mapped the entire universe that we can observe and reconstructed most of its history, except at the very beginning. In addition, we have achieved exquisite understanding and control of matter, ordinary matter, in all of its phases, or actually many of its phases, some we haven't yet discovered, down to the nanoscale of atoms. This is unbelievable. One looks back over 50 years, the amazing achievements of basic physics. I like to say, however, that the most important product of knowledge is ignorance. Sometimes people are a bit shocked by that. What do you mean by that? And of course, by ignorance, I don't mean the ignorance that is exhibited by most of our politicians, or that leads to racism, bigotry, hatred, war. What I mean is questions about the real world, the universe, nature, and especially new questions that can be answered by the scientific method, by observation, by experiment, and by theory. Now, knowledge advances in physics, leading to successful understanding, theories that are well tested by nature, raise questions that couldn't be raised before you had enough knowledge to realize that you were ignorant. This is the way I picture it. We exist in a bubble in the sea of ignorance, which I'll come back to at the end of my talk, pushing outwards into this bubble of ignorance. we are aware of what exists at the frontiers of this bubble of knowledge. But we're not aware of the ignorance that exists somewhere far out in the sea. We need to have enough knowledge to be able to formulate good questions. We have to be able to observe this ignorance. So in developing our knowledge and the understanding of nature, among the rest, we are developing new questions that can be answered by the scientific method. The questions we ask today, in my opinion, are much more exciting in a deep way, for sure, than the questions that were asked when I was a graduate student. Most of those have been answered, but they're new questions. And that's what pushes science forward. So at this institute, basic science, in many different fields, including physics, this institute operates at these frontiers. So I'm going to discuss a few of these frontiers. On the largest scale possible, cosmology, 10 to the 26 meters, size of the observed universe, down to the smallest imaginable scales so far in physics, so-called Planck length. I'll discuss a bit about black holes, which are kind of a macroscopic scale. The black holes we observe in the universe are around size of thousands, 10,000 meters. Then we'll come to ordinary matter, built the behavior of atoms and molecules, and some of the frontiers of condensed matter physics, which explores the frontiers of our understanding of the various phases and structure of matter, with very interesting possibilities of harnessing quantum mechanics to increase our computing power. And then we'll go to the smallest imaginable scales, that where string theory flourishes or is necessary, perhaps. So 60 orders of magnitude, starting the largest scale, way back in time to when the universe was very small, say. And our picture of the universe breaks down. We have a photograph of the universe as it existed roughly 300, 400,000 years after the Big Bangs, the beginning, whatever that means. This is what it looks like, a rather boring, homogeneous sphere of radiation and matter. But gravity clumps those little perturbations in this homogeneous universe to form strands of matter and galaxies eventually. And we, astrophysicists, astronomers, with our understanding of atomic and now subatomic forces, are able to reconstruct the history of the universe based on both theory and observation. We have a pretty good, we believe, well-tested picture, history, quantitative history of how the universe evolved from this soup of hot radiation to our existing universe full of many galaxies and black holes. And what we don't understand is what happened at the beginning, the so-called Big Bang, if you want, or where the universe began, whatever that means. There, all of our approaches break down, so that's clearly the frontier of knowledge. And the ignorance is, how did it begin? We'll come to that. At the microscopic scale of atoms and nuclei and subnuclei, as Rajesh mentioned, we have constructed around 50 years ago, completed the goal that has occupied physicists for millennia to construct a understanding of what are the basic constituents of matter, what is matter made out of, and how does it interact with itself to form structures like atoms, molecules, and nuclei. I don't have that much time. So to summarize, the standard model is quite simple. It's a list of particles that largely have been discovered experimentally. They turn out to be particles we call quarks. And the simplest of these families, are the up and down quarks that exist, make up the neutrons and protons that make up the nuclei that make up the center of the atoms that we are made of. And of course, in addition, there's the electron, which revolves in a simple way around, there's a cloud around the nucleus of atoms, and its friend, the neutrino, another pair. And then over the years, the last even more than 50 years, we have discovered, not predicted, discovered, two other families of quarks, John Strange, top, bottom, and together with two other families of electron-like objects, muon, tau, and their neutrinos. So we now believe that, at least to a very good approximation, all matter, well, almost all matter, is made of quarks and leptons. But even more important, we understand the forces that act on these elementary particles, point-like elementary particles, that explain the structure of atoms, as well as the structure of the nucleons that make up the nucleus of atoms. The nucleons turn out to be composites of quarks, and the atoms are composites of nucleons and electrons. Atoms are nuclei and electrons. Molecules are composites of atoms. The forces we ended up proposing around 50 years ago in a spurt of just theoretical discovery, which put together all the experiments and observations that had been done in the earlier part of the 20th century, turned out to be a generalization of the force, the force that was known to Maxwell. In the 19th century, the great triumph of physics, 19th century was the discovery of electricity and magnetism, the union of those in Maxwell's theory, which explained electricity and magnetism as due to a field whose source, a field that permeated all of space, and whose source was the charge of particles, like the electron. Turns out that the other forces that act within the nucleus of atoms are generalizations of this same kind of electromagnetic force, except that they have more than one charge. So within the atom, within the nucleus, within the atom, it's essentially just the force of electricity and magnetism. But within the nucleus, which was very mysterious, and the charges that govern the forces that act within the nucleus, and even the elementary constituents, the quarks, were hidden from us by a mechanism I'll describe. But in the end, we understood that these two forces were generalizations of Maxwell's electromagnetic field theory. The strong force, which is the force that holds the quarks actually permanently within nuclei, is due to three kinds of charge that exist among the quarks. The quarks don't just have one charge like the electron, they have three charges, and we call them color. Okay, what the colors of the Indian flag are green, if I'm right, green, white, and what? Orange? Yeah. Saffron, green, and white. So those are three colors. So each of these quarks here, up and down quarks, there are actually three of them. There's a red, well, hey, green, saffron, and white up quark, and green, down quark, and so on. It turns out, we'll discuss the dynamics of a theory like electromagnetism, but with three charges, is very different. The weak nuclear force, which is responsible for radioactivity, turns out to be a force that changes one kind of quark into another, up kind of quark to a down quark. So up and down, we call flavors. They're a kind of charge, but only two charges. Similarly, changes an electron to a neutrino. And that's the origin of radioactivity of nuclei. So we have three forces at the core very similar. Suggesting perhaps they're all the same in some sense. But they appear very different. That's why it was so hard to find them. In addition, there's a final component of the standard model, which you might have heard of, the Higgs mechanism, or the Higgs particle, which was discovered about a decade ago. And it plays an important role in the weak force and explains why it's different, for example, than the strong force, and why these elementary quarks and leptons have a mass at all. Now, this theory is quite remarkable. It was essentially completed almost 50 years ago, and it's been tested literally in thousands of experiments, sometimes with incredible precision, often with precisions around 1% or less. It seems to work. We don't see any real violation, or one that can't be easily incorporated in simple extensions of the standard model, for example, to explain how the neutrinos get a mass, to all over the universe. And we look out with our telescopes and we can see and test our predictions that matter everywhere in the universe obeys the same law. And as I will discuss momentarily, we seem to be able, with no problem, to extrapolate this theory to orbit even smaller distances than the size of the proton, the size we can currently explore. It's an amazing theory. In some sense, it could be pretty complete, or 60 orders of magnitude, from this biggest scale to the smallest scale. It's amazing accomplishment of 2,000, but really only 400 years of physical exploration. Okay, let me return now to how did the universe begin, before I come back to the standard model. There, the question is really, how far can we probe? If we really want to understand the beginning, we had better be able to test the beginning, to observe the beginning. And that's pretty hard because of this ball of radiation 300,000 years after the beginning that prevents signals, except perhaps gravity waves or neutrinos, but it's very difficult to do. But then there's a much more fundamental question is, can we really determine how the universe began? This used to be a religious question, a philosophical question. Now it's a scientific question, for sure. But physics has never had to determine the initial condition. Physics typically, what physics is supposed to, given some initial conditions, predict the future. That's our business. But in the case of the universe, we have to know what the initial conditions are, and we can't prepare them now to predict the future of the universe or even the current state. This is not a question that physics has ever tried to answer before. It's only recently become a truly scientific question. So we don't really know whether physics is capable of doing it. And it's very tricky. You start thinking about what do you mean if you had a theory that predicted the beginning of the universe? Was there a time before the Big Bang? What is it? Challenges clearly our notions of space and time. So much so that some people say there was no beginning. The universe was cyclic. It contracts, expands over and over again. Einstein believed the universe was static originally, never changed. But now we know the universe is expanding, and we can extrapolate back to something which we could call the beginning, but we really have no idea what that means. There are other issues in the universe which are at the frontier of knowledge, and the questions drive us. For example, the energy and mass content of the universe. So astronomers discovered that there was a lot more mass in the universe than we could see, like stars that radiate light, so we see and know how much mass there is from stars. But dark matter, which they discovered, therefore, does not radiate, does not interact strongly with us, with our kind of particles, the standard model forces and particles. Otherwise, we would have seen it. The only effects that we know about this dark matter is like any form of matter must attract other matter. So we see light, which carries energy, in a sense is matter, particle, like photon, and gravity really attracts energy. We see light bending due to some kind of dark matter that fills the universe. And we can map that out. Astronomers have mapped it out. Plays a crucial role in understanding how the universe evolved, how galaxies form. First, the dark matter, the dark matter attracted itself and created a kind of clump into which ordinary matter, the little that's left, normal matter here, just the stuff that we're made out of, fell into these dark matter clusters. And that's a big part of our understanding, successful quantitative understanding of the evolution of the universe. But what is dark matter made out of? We've never seen, and there are many, many possibilities. This is the way we envisage the galaxy today, as I said. Ordinary matter in a big, much bigger clump of dark matter, which we so far only observe indirectly. This is the kind of map that astronomers can create of the distribution of dark matter way out in the universe. And the way they do that is by gravitational lensing, by the fact that light coming from objects behind this strand are bent by the gravity of this dark matter. So you can directly map out the dark matter distribution. But what is it made out of? We would expect, because of relativistic quantum mechanics, which is essential to our fundamental understanding of the nature, that dark matter would annihilate with other anti-dark matter. Can we see dark matter annihilation in space? Or can we produce in the laboratory? Again, because of relativistic quantum mechanics, any kind of matter, there has to be antimatter. So you can produce dark matter and antimatter if you have enough energy. And we've got a lot of energy in these high energy accelerators and have been looking for producing dark matter for years unsuccessfully. Another possibility is dark matter must, unless, even gravitationally, interact with other matter. And so we could and do create laboratories way underground where nothing much is happening, and look for dark matter coming in. And according to our expectations, there are lots of dark matter flowing through you all the time. You don't feel it or detect it because it interacts so weakly. But if we have a lot of it underground, nothing else is happening, maybe people have been trying to detect dark matter flowing through the laboratory. For many years, I really expected that this problem would have been solved 10 years ago, but it still hasn't, and it's sort of at the forefront of experimental astrophysical exploration of the matter content of the universe. And then the universe also is full of some other kind of stuff that carries energy and pressure, which is very weird. It's the only kind of energy and pressure which looks the same to any observer, in accord with Einstein's basic principle of special and general relativity. And for that to happen, this possible stuff has to have energy and negative pressure. Negative pressure is pretty unusual, right? Ordinary gases carry energy and pressure, like the air inside of a gas of atoms moving around inside a balloon. There's the kinetic energy of the atoms, but pressure, you push on the balloon, there's pressure that resists your pushing. The dark energy, it's negative pressure. And the effect of that in Einstein's theory, where mass and energy curve space-time, is that dark energy of this sort, if there, would make the universe have accelerated expansion. The expansion we see of the universe, and we now quantitatively can measure, is accelerating. The rate of expansion is increasing in time. So it could be that so-called cosmological constant that Einstein actually introduced originally because it was consistent with his theory, and he could use it to try to keep the universe static. Once it was observed that it was expanding, he threw it away. And we all believed it should be not there, because turns out to be very, very small by 120 orders of magnitude in natural units. And we could never, and still can't imagine explaining such a small number, so we assumed it wasn't there, but it is, according to observers. Is it really a constant? Will the universe continue to have accelerated expansion forever? We don't know, and there's some recent suggestive results that it's slowing down. The acceleration is slowing down, maybe. Too early to tell. This is a very exciting, because it doesn't address the question of how the universe began. Which we can't experimentally test directly, but it does address the question of how the universe will end, which is equally interesting. And in principle, asymptotically, we can test. Coming down and distance to black holes. So black holes, sure you've all heard about. Astronomers and physicists have realized that these objects that Einstein's theory predicted and he never believed in, and most astronomers never believed in, exist throughout the universe. In every galaxy, including ours, there's a big black hole. There's small black holes whose mergers, collisions, we can now observe and study because they create gravitational waves. So this is a black hole in the center of our galaxy, which you can't detect directly because it doesn't radiate, it's black. But you can detect its effect on stars nearby, mapping out their orbits and deducing the nature of the very massive objects that exist in the center, and it's very black. This was part of the recent Nobel Prize for the discovery of the black hole at the center of the Milky Way. These black holes are very dense gravitational objects, so they attract things, and they are believed to be the center of very violent events in the universe, like gamma ray bursts, which are observable. And most exciting in fundamental physics, verification of the weird effects of black holes, was the observation of gravitational waves, which are very consistent with black holes actually merging. This is the LIGO detector, which is the interferometer in Louisiana in the United States, and there's another one in Washington. And what they do is measure the teeny distortion in the length of this tunnel and this tunnel, which carry light rays, which interfere here. So this is an interferometer, big one. If the gravitational waves that were observed, which are believed to be due to the collision of two black holes, produce a wave which travels billions of light years, billions of years throughout the universe, hits us, it's a wave of gravity. Gravity is the curvature of space-time. So the space and time are changed at these, and since this interferometer consists of two legs, this one is changed, increases, this one decreases, or vice versa. The teeny change in the length of these interferometers of the order of 1 part in 1,000 of the size of the proton. And they can detect that interference. Amazing. And that was the first observation of gravitational waves about 10 years ago. And since then, gravitational wave astronomy, using these gravitational waves, which are produced in a variety of ways. Of course, I've just produced a gravity wave. Right? I'm moving the source, energy, mass, the source of gravity. And so I'm slightly curving in a wave that propagates space and time. But that's totally unobservable. It's much too small. But when two massive black holes, each of whom are of the order of, say, 50 solar masses, mass of the sun, come together, we actually have a theory which can predict what will happen. And the prediction is that they will produce a wave. We have the equations. You can see what kind of wave it would predict and match that to the data and learn a lot about the black holes. Very exciting. Not only black holes, in one fantastic event about 8 years ago, they observed gravitational waves coming from what they concluded were two neutron stars, very dense, ordinary stars, but very dense, collapsed neutron stars. And the advantage of that is that neutron stars are not black, they emit stuff. So there are other signals from that event in not just in gravity waves, which interact very weakly, but light, X-rays, ultraviolet, optical, infrared, radio waves. This collision was seen first in gravitational waves, and then they told all the astronomers in the world, something interesting is happening, and it's around there. And in the next few days and weeks, an amazing study of this event. And, oops, let me go back. Amazing study of this event, from which just one actual verified event of collision of two neutron stars. They were able to learn a lot about how elements, heavy elements, were created in the history of the universe. Because in the beginning, there was just hydrogen, just protons and low mass atoms, which are produced in nuclear reactions. How do you produce gold and lead and silver and uranium? It takes a whole lot of processes. And it appears that these processes have to do with supernova, which lead to neutron stars. And anyway, this gravitational wave astronomy is beginning to teach us a lot about the cosmology, the cosmological history and the astrophysical processes of the universe. Okay, let's now go down to an even shorter scale, that of atoms, which are only a nanometer. And what really has changed, we just had this conference in Bengaluru, QIB, the next decades to come, new technology based on quantum mechanics. Of course, the whole world is based on quantum. What really has changed and makes this so exciting, not just to basic science, but also to applied science, is that the two are beginning to coalesce at the frontiers. So experimentalists now can manipulate, and theorists can understand matter at the atomic scale. This is actually an array of atoms that one can create experimentally in the lab and this kind of corral and study the physics in this kind of, which is kind of interesting theoretically, but just an example of the power of current experimental physics. There are many such applications of that ability to understand, manipulate, and control. For example, we can create new forms of matter, either in many ways, but in principle, who knows when, we could create macroscopic forms of matter by atom. And in my opinion, that's a vast new frontier where we're no longer limited by the astrophysical processes that led to the kinds of matter we have on Earth. For example, graphene, which is a two-dimensional array of just carbon atoms, carbon being such an enormously interesting atom. Things we can make out of carbon include diamonds, which are kind of nice, as well as people, which are even nicer. The use of these new materials is there's some obvious uses that people are trying to develop rapidly, quantum sensors, and what I'm coming to now, quantum computers. But I really believe that the possible uses of the new materials and the realm of new materials itself we're probably way underestimating what is possible and what will turn out to be useful. One thing that's kind of obvious and has driven a lot of the research and potential applications is quantum computing. We're running out of Moore's law at the quantum scale. And the hope is to construct quantum computers. Quantum computers, theoretically, we understand can be, in certain cases, demonstrably, much more powerful than classical computers, which are based on classical bits of information, zeros and ones. As you know, that's all you need to construct a computer. Classical bits you could think of as an electron. An electron has a spin, it rotates kind of. Spin can be, if you measure it, this axis, it's either up or down. So you can use quantum devices like electrons to construct an analog of a classical bit, 0 and 1. So it's a physical object, it'd be 0 or 1, but it differs from a classical bit because it can be, the spin can actually be in any direction. Okay? And not only that, in quantum mechanics, you can add, superimpose these different 0 and 1, different states. So in a sense, a system like an electron, which is a two-state system, like 0 and 1, actually can be in a much larger space with an infinite number of directions it can be. That enables these computers both to store much more information and manipulate much more information and in a parallel fashion. The problem is, which I lost immediately, is that the quantum states that are necessary to be better than classical states, to harness the power of quantum qubits compared to classical bits, you need to preserve this quantumness. Classical physics, now that we're used to with zeros and one, is an approximation to quantum physics, and a very good approximation in the macroscopic world, because once you take quantum states, couple them to the environment, and you can never isolate completely anything from the rest of the world, very rapidly loses the quantum special character, the coherence, we say, of these quantum states. And so any contact with the environment typically turns the quantum state into a classical state, and you lose the power. So people are trying very hard to preserve that coherence, succeeding at the very preliminary level. And personally, I think that will succeed. How long? 20 years? Who knows? When asked that question 10 years ago, I would have said, or 5 years ago, I would have said 30 years. The progress is quite remarkable. It's an enormously challenging thing, but nothing in physics that we know of prevents this from happening, so it will happen. But perhaps even more interesting is the discovery of new kinds of matter, either the creation of, or the discovery of new forms of matter. And that's proceeding, that's a much more, in some way, less of a quantum computing problem, but a basic physics problem, the nature of matter. So all of these prospects are enormously exciting. Now let me go even further back to the subnuclear scale, where we have the elementary, the standard model of elementary particle physics. Oops, I already did this and I screwed up. I want to discuss one force that Rajesh brought up. I can't resist bragging about QCD. So QCD is the strong nuclear force, as I said, has to do with the fact that there are 3 charges. Why does that matter? Well, it turns out, so this is a picture, an illustration of a quark and an antiquark. Red quark, red antiquark, say. Now, classically, and in the classical theory of quantum, classical chromodynamics, these would obey Coulomb's law with a 1/r² attraction, and you could pull the quarks away and you could pull them out of the proton like we pull electrons out of the atom. We pull them out of the atom, we make them run in wires. We have the Industrial Revolution. Why can't we do the same with these quarks? Pull them out of the proton and make them run in wires or who knows what. Well, the difference really is that because there are more than 2 kinds of color, or 3, the field that carries the force and the quanta of the field, which in the case of electromagnetism is light. Light is the quantum particle of the electromagnetic field. The analog of light we call gluons. But because there are 3 colors, turns out there are 8. 3 squared minus 1, don't ask me why. Gluons. And they have color too. And they experience the force. Light doesn't. Light doesn't interact directly with light, certainly not classically. But gluons interact with themselves. So what happens is that these quarks are situated in empty space in the vacuum. And in quantum mechanics, the vacuum is a very complicated thing. It's full of fluctuating quantum fields, quarks and antiquarks, electrons, anti-electrons. But in the case of quantum chromodynamics, also fluctuating chromodynamic fields, gluons and anti-gluons. And they have a big charge, turns out, and the big effect on the nature of this vacuum, which is a kind of medium that the quarks are in. And so instead of having these lines of force follow the laws of simple classical electrodynamics, they are squeezed by the vacuum, the fluctuating vacuum, this medium, to form a flux tube. And now you just calculate the force in the same way you do in electromagnetism. It does not decrease as you pull the quarks apart. Not only that, it gets weaker when the quarks are together, which is the phenomena of asymptotic freedom that led to this picture, to this theory. And that's the secret of the strong nuclear force. This is an actual illustration of a calculation of the force. What happens when you try to pull 2 quarks apart in QCD? It's a numerical solution of the equation. And because of that, as I said, the energy it costs you to pull them apart continues to increase no matter how far you pull them apart. And that confines permanently quarks within nuclei. Now, in the proton, you actually have 3 quarks. And there, when you try to pull them apart, these fluxes confined in this kind of triad, which also explains their structure. What do I mean by explain their structure? So when we developed this theory, what I really wanted to do, the dream was calculate the mass of the proton, the mass of the neutron, the mass of the dozens of hadrons of strongly interacting particles. That's what a theorist is supposed to do. A theory is strong if it can calculate everything. That's the goal of basic fundamental science. To arbitrary precision. Well, it turned out to be very difficult. And it's taken 40 years roughly. But this is the situation today. Quite remarkable. All of these are observed particles. Here's the proton is here. These are, so you can even calculate them very small, roughly 0.1% difference between the neutron and proton masses. These are states of very heavy quark composite particles. Quite remarkable. However, there's a very strong lesson to be learned about the power, as exhibited here, and the limitations. Why did it take 40 years? This is a numerical solution of the equations of QCD. To have this kind of accuracy required an improvement of calculation by 18 orders of magnitude. 9 of that is due to Moore's law, due to the fact that in 40 years, computing power has increased by a factor of 1 billion. Without that, these computations would be impossible. But another factor of 1 billion came from the continued efforts of basic scientists to improve how the calculation goes. All sorts of finite size effects, Young-Akara symmetry, improved Lagrange, many things, which you can estimate to be of the order of a factor of 1 billion. So to do this calculation, was the basic direct approach 40 years ago till today, took 40 years and literally thousands of men, women, hours, hundreds of people working perhaps their whole careers. But it can now be done. And well, the nature of physics is that people will try to increase the accuracy of these kinds of predictions beyond the 1% level that's here to 0.1%, 1/100%. But we can also, as theorists, do more than just calculate the properties of the particles we observe in nature, but speculate as to what lies behind. How do the forces unify in particular? So the standard model, remarkably, is based on 3 forces, which are all the same except for the number of charges and the Higgs. But if you just think about the charges, the strong and the weak, which are both asymptotically free. Electromagnetism, which is the opposite. Electromagnetism, you bring the charges together, the force gets stronger. Now, which is what everyone expected, would always be the case. And that suggests that you could unify these theories. You might, at least as far as their strength goes. The particles also fit together completely nicely, so that it's completely consistent that at high energies, there's only one kind of force and one kind of particle, family of particles. And even initially, with very crude understanding and very crude measurements, seemed to be that these forces came together at a very high energy. And the particles could fit together in nice ways, and one can easily make unified theories, which made predictions, which were wrong. But this, in my opinion, is still the most important clue about what we have at very high energies, very short distance. And it's made even much more important by the fact that gravity, a very weak force at the size of the atom or the nucleus, it becomes an equally strong force in the same region, this fundamental length, the Planck scale. And that is one of the important clues that enhanced the interest in string theory, which is the only way so far we have of combining gravity and the other forces of nature in a natural, consistent way. So, big question, is string theory the right approach to construct the unified theory of gravity and the other forces? It is in principle, we know that, but is it actually the way we describe our universe? We don't know. There are too many solutions, and we don't know what picks the right one. But since string theory has turned out, as far as we can tell, to be a completely consistent theory of quantum gravity and the other forces that we recognize in nature, we have some hope that we can understand finally gravity, quantum gravity at the scale, perhaps, where the fluctuations of space and time, which has become a quantum object in Einstein's approach, and are uncontrollable in Einstein's theory, that string theory might go beyond Einstein's theory and explain many things. But string theory has raised even more questions than it answers. For example, the nature of space and time. At the very beginning, the string theory turned out to only exist, make sense in more than three-dimensional space-time. And it was known from Einstein onward that there could be more dimensions of space-time as long as they were small enough so you couldn't see them. So at every point in space, there might be a complicated higher dimensional space attached with each point, and you'd need very good microscopes to see that. And we don't have such microscopes at this scale. Particle accelerators are microscopes. That's how we study the structure of the proton. But to get to this scale, we would need microscopes which are 20 orders of magnitude more powerful. So there could be, and in fact, we understand that actually there are solutions. There are solutions of string theory which have 6 compact dimensions this type. And it's really quite beautiful because the nature of the forces that explain what the kind of Maxwellian-like theories, gauge theories we have, and the kind of matter that we observe, the quarks and leptons, and the value of their masses, all of these are issues that cannot be predicted by the standard model, are determined sort of geometrically by the shape of the hidden dimension. So but again, it turns out, okay, that's great, but you have 10 to the 500 or 1,000, or actually an infinite number of such solutions. So, and they're not trivial. One of them might actually describe the world we measure directly, but we don't know which or why. One of them should. The other thing a string theory has given us is a real we now supposedly have a theory of quantum gravity. We can really say what happens in black holes. Was Hawking right? Do black holes violate the unitarity, the law, the conservation of probability of quantum mechanics? You drop entangled pairs or you drop things into a black hole, do you lose information? Well, that has been an issue for the last 50 years as well. We actually think that string theory, ideas that have come from string theory and are perhaps even more general than string theory, solve that problem by remarkable dualities that we understand now exist between quantum gravity and ordinary quantum mechanical systems. And the most famous of these dualities, which are complementary ways of describing the same physics, is between ordinary quantum mechanical systems, like the standard model, very similar, and strings in a curved space-time in one higher spatial dimension, whose boundary sort of hosts this four-dimensional theory that we understand. It's like the standard model. So we can translate aspects of this well understood in certain regimes, quantum mechanical, non-gravitational system into string theory or quantum gravity in a higher dimensional space. This has dominated speculative basic physics for the last 30 years now. And it really has resolved, most of us think, this paradox that Hawking claimed, that black hole formation, evaporation violates quantum mechanics, because we can construct analogs of black holes in this higher dimensional space as normal physical systems in 4 dimensions, in cousins of QCD. In QCD, if you collide a lot of particles together, kind of to form a black hole, you're not going to form a black hole because in QCD, there's no gravity. So space doesn't get curved. What does happen, however, is that there is a new phase of matter that is constructed. You have all these nucleons, lots of energy, they melt, and the quarks come out, and you have what we call the quark-gluon plasma. And then this plasma expands, cools off, quarks go back in and form nucleons, and what you see eventually are particles. This we can do in the laboratory, and we have done. It's called the heavy ion collider. It's done at CERN, it's done at Brookhaven. Collide very heavy atoms, gold atoms, lead atoms, nuclei at very high energies, form for a very short amount of time this new state of matter, quark-gluon plasma. And that is what is exactly analog to a black hole here in this dual description of quantum gravity, where matter comes together, something energy comes together, forms a black hole, Hawking radiates, the black hole eventually disappears. Since we believe, not prove, but believe that these are exact descriptions of the same physics, that means that this black hole description, which we actually perform in our laboratories around the world, and does not violate information, is well described by quantum mechanics without losing information. The same must be true for this. And the question, and Hawking agreed, as more or less everyone else has, but the detailed question of how that information gets out of the black hole and so on, and what is the space-time description of that, remains one of the central areas of study nowadays. Okay, I'm not going to discuss this. But coming back to space-time, string theory has really challenged our notions of space-time. This duality actually was a duality between theories in different dimensions. One was 3 plus 1, free space 1. The other was 4 plus 1. But all the traditional understanding of space and time, one of our basic concepts, string theory challenges. We always think of space, well, originally we thought of space as being Euclidean space, period. Now we know that it's dynamical, but in classical relativity, you can't tear space-time. You be a smooth geometrical structure. Not in string theory. You can go through singularities easily. String theory, in ordinary space-time, there's a notion of topology, as you all know, which you can't change. But you can in string theory. In ordinary space-time, you have a fixed number of dimensions. But in string theory, it depends on how you look at it, what questions you're asking. So we sort of imagine and have for many years that we sort of expect that in some sense, and we really don't know exactly how, space-time is emergent. It's a good concept that, except when you get close to the Planck scale, or except when you're trying to discuss certain aspects of black holes, both cases where quantum gravity is essential. But boy, that is a difficult question. If you imagine that the fundamental formulation of physics in the end doesn't introduce space-time, that's an emergent, it's a property of the effective theory that is valid for large distances or weak gravitational fields. And though in the language that replaces it, what are the rules of physics without space-time? Space physics is, you give me this situation now, initial conditions, I'll predict what's in the future. How do I even formulate what the rules of physics, quantum mechanics are at play? Space and time aren't fundamental concepts. Okay, the origin of space, what is space-time made out of, et cetera, et cetera, et cetera. That's really difficult. Do you really expect these people here at ICTS to solve these problems? Should they be encouraged to do so? So I'm always comforted by Einstein, who tried and failed, by the way, to do this kind of thing. And he said the successful attempt to derive delicate laws of nature along a purely mental path, he meant not, experimental observation, but doing what some of us do, theorizing. But by following a belief, however, that's what motivates us, gives us confidence in the formal unity of the structure of reality, encourages continuation in this speculative direction. So, he was successful in his theory of gravity, thought it could be done, but reminded us, of course, that the dangers of this, everyone vividly must keep in sight who follows it. Okay, I have time. What Drupal say? I'm often asked for such a thing, which is, describes the outlandishly arrogant dreams of fundamental physicists. Are you ever going to end up with a final theory? And are you just going to continue to do this? The frontiers grow, more questions. Is it going to end forever? Or there might be a final theory. Is that your goal, a final theory? Is there a final theory? Well, I'm going to discuss this question about whether there is a final theory and what would it mean. There are many reasons why there might not be a final theory, or there might be a final theory, or we might not be able to find it, even if there is a final theory. More importantly, we might lose the will. So let me discuss this. So first, I'd like to put this, as physicists love to, in geometrical terms. So we're going to describe a model, a geometrical model of knowledge and ignorance, which we started with. In that context, define what a final theory would be. So you all know, of course, the onion model of knowledge. Knowledge is a reality. The world is an onion. You peel away the layers to get to the core, and that's it. This model brings tears to my eyes. And it doesn't explain anything. It's quite different than the model I started with. We live in a sea of ignorance. We're inside, not outside. Probing out, not in. Now, that's a good model, and it'll predict something which is verifiably true and give us information. Yeah, that's what a model should do. So in this model, we have some kind of space, compact, this model can be elaborated. The simplest form is a kind of sphere of knowledge expanding into the sea of ignorance. All right, and so knowledge obviously increases. That's the goal. We increase knowledge. Encyclopedias get bigger. And that's what's happened over the last thousands of years, especially the last 400 years. That knowledge is all available in libraries, now in Wikipedia, or Ask GPT. So the volume of knowledge that we can access and we build on goes up. But also the volume of ignorance goes up. Knowledge leads to more ignorance because ignorance is stuff here at the boundaries of knowledge. And as we expand, there's more ignorance that we're aware of. So there are a lot of areas of ignorance out here. These are the unknown knowns, unknown unknowns. But ignorance, the kind of ignorance I'm talking about is the known unknowns, and that increases as we move outward. So this explains exactly something you all have experienced, especially maybe the young students who find it depressing. The more they know, the more ignorant they become, the more aware of what they don't know. So that's very different than the onion model, anyway. And wisdom, which in some crude sense is the ratio of knowledge to ignorance, also increases. Because the volume, as you know, increases faster than the surface area. Okay, so now we have a geometrical model of knowledge. We can apply it to final theory. Can we construct a final theory of physics of nature? So in this model, is there a finite amount of ignorance? A final model would be one where we run out of ignorance, answered all the questions. This has happened, and it's happened in the exploration of the Earth. So this is a map, a Eurocentric map, by the way. Notice India is not even. India is one of these unknown unknowns. So this is a map of the surface of the Earth. This is sort of the knowledge. This is the ignorance. And for many years, centuries, people explored the surface of the Earth. But the Earth is round, as you all know, and the surface, eventually, we explored the surface of the Earth, the whole surface of the Earth. And up to a distance of maybe a meter or so, we have Google Maps, gives us a map of the surface of the Earth with some resolution, and it's over. There's a final map of the Earth, and you can access it on Google Maps. Exploration societies closed down. It was the end of that field of scientific exploration. So the real question about whether there's a finite theory in this geometrical model is the sea of ignorance compact? It could, and by the way, I'm completely agnostic. I don't. Could be either. It could be unbounded and infinite, like people used to think the Earth was. And then knowledge could expand forever into this infinite sea of ignorance. Or it could be compact, like the surface of the Earth, in which case eventually we would run out of ignorance and have a final theory. How can we answer? Well, there's no sign of curvature, at least nowadays. As we continue to explore, more and more questions arise. So at the moment, it looks flat or unbounded, but who knows? There would be evidence, by the way, of curvature, of compactness. What would it mean? It would mean eventually we'd start running out of questions. We just have to ask the same kind of questions in more detail with more precision over and over again. But that so far hasn't happened. I think we would notice it if that happened. Well, if you actually had this final theory, would that be the end of physics? Well, here I have to admit, It wouldn't by any means. Most of physics does not do the kind of thing I've been talking about for the last hour. We do believe that physics is reductionist, that the fundamental laws in principle would lead to the effective theories that we actually use to describe the observations of a very complex and interesting universe. So it certainly wouldn't be the end of physics. But the final question is, and we just might be too dumb to achieve a final theory, if it exists even. I've been, I like to say, unable to teach my dog quantum mechanics. We're quite aware that our fellow species from which we evolved in our 99% same DNA are simply unable to comprehend the mathematics and the thinking that enables us to understand the science that we have understood over the last millennia. Why? I mean, it's really incredibly arrogant, a typical human quality, to imagine that we are somehow, we have evolved to understand quantum mechanics, string theory, the origin of the universe. That was evolutionarily selected. We're so far above our friends, the dogs and the apes. Well, so that is a worry. And we can well imagine that we are, like all the other species, have inherent limitations. So being an optimist, I think that's not a problem for a variety of reasons. One is that what really picks us out from all the species in the world is language. There's enormous social utility, evolutionary utility, but also obvious utility in understanding the world. And the highest form of language is mathematics, which clearly has infinite capacity. But even ordinary language has infinite capacity, as Chomsky discussed, an infant who has somehow the ability to pick up language just by listening to its parents. And then, as Chomsky said, make sentences, even as a first year, that no one has ever made before. That's infinite capacity. So there is an infinite capacity, that we have, that distinguishes us from all the other species. And that might be enough, but it might not. There are many kinds of infinity. This might be too small, infinite capacity. Again, there's experimental evidence. There's no sign currently, even though we're asking these, what seem to be incredibly hard questions, conceptually hard. But there's no sign that we're faced with questions that can't be answered. So what if there were questions that we can't answer? Well, that we would begin to notice. Graduate students would take longer and longer to get to the frontiers of knowledge. And they wouldn't get beyond it. There wouldn't be progress. That's not what has happened in the last 400 years. So maybe there are questions. Maybe the origin of the universe was the nature of space-time. What is space-time made of? Are such questions. But so far, there's no evidence, especially with young, brilliant students. They, even though it appears that they need to know more and more complex mathematics, and we're getting close to these impossible questions, still around the middle 20s, they're ready to go and make significant contributions at the frontier of knowledge. Now, this was, no, I screwed up. So, so can we go on forever in the search of the final theory? We might find a final theory, but more importantly, we might, and by we, I mean society, the world might lose the will and means to go on, because it does appear that continuing in the direction of these fundamental basic questions about nature, it's more expensive, takes longer, and we might very well lose the will and means to go on. That's my biggest worry. But here I appeal to David Hilbert, who on his tomb said, "We must know, we will know." And that's it.
Thanks very much for taking us on that grand tour of cosmos, the ideas, and everything else, and the final will to proceed. So especially for the young students. I think we are running a bit late, so I think maybe we'll just take. I mean, there are many questions in the chat as well, because this is being live streamed. Let me see if I can just pick one. But in the meanwhile, is there from the youngest members of the audience? No, from some very young people. Yeah, if there's one very young person who wants to this thing, well, anyone younger?
State your age.
Yeah, maybe, okay. You can go ahead. Just wait for the mic.
Okay, so Professor Gross, first I want to thank you to come to my city and share your incredible, valuable knowledge with all of us. And also, today I believe that we all truly stand on the shoulders of giants in theoretical and practical physics. Giants and titans like you have brought us to where we are now.
Yeah.
So,
yeah.
I actually have a couple of questions.
We can take one. Just take one, please.
Okay, so Japan has recently, like over the last 15 or 20 years, have conducted many like proton decay experiments. So do you think that we are any closer to discovering proton decay than we were like in the past half decade?
I certainly hope so. So as part of, if you have a unified theory of all these forces, then protons will be unstable, decay, if you wait long enough. We know they live at least experimentally of the order 10 to the 34 years. It's really hard to wait that long to see the protons decay. But if you take enough of them together, maybe in a few years, one of them will decay, and you could set it up so you could carefully see that. People have been trying since 50 years ago and failing, which means that the lifetime is longer, which is not inconsistent with this unification happening close to where gravity becomes important. On the other hand, that's very disappointing because proton decay would give us the most direct way of observing physics at this incredibly high scale of energies or short distances. So I really hope those experiments discover proton decay, but it could easily be many orders of magnitude beyond their reach, unfortunately.
So we'll just take one question from the online as well. There are many nice questions, but one which is about the cosmology is lambda CDM, which is just a name for one of the models that we have, the kind of standard model for cosmology. Is lambda CDM the most perfect model we have to explain the universe until now, or are there other refined models that resolve the Hubble tension? The Hubble tension is something, maybe David, you want to say?
Well, lambda CDM is an incredibly successful standard model, if you want, of astrophysics, of cosmology. It has a certain number of parameters. It does not explain how the universe began or how it started inflating, which is part of that, or how it will end. But it's incredibly successful. There are, as always in physics, some questions, observations which might or might not contradict a theory. In the case of cosmology, there are really two such things. One, I alluded to the fact that there are some reports that the dark energy, the cosmological constant, might be slowing, the accelerated expansion of the universe might be slowing down. And the other is two groups that are measuring the Hubble constant, the rate of expansion of the universe, get results that are experimental results that are in contradiction. They simply don't agree. That's happened before, and especially in cosmology, and where you are doing only observations and not experiments. You can't go out and change what you observe. That's much more powerful. And so it's often happened in cosmology, in particular the Hubble constant, the rate of expansion of the universe, used to be when, 30 years ago, 40 years ago, there were different groups that claimed it was different by 100%. Now the difference is much smaller, but significant. And some people think this is a real problem, a crisis, a necessity of changing the theory. And some people say, okay, there's something wrong with one of the experiments. And who knows?
Yeah, the jury is still out.
There are these two problems. Both, by the way, have to do with the expansion of the universe. And it could be that both are related. But one, we really have to wait till the experimentalists decide that there's a problem. And two, it's a very interesting connection. They could be, but nobody has a good idea that I've heard of how these two issues might be connected.
But in general, it's a good thing to look for tensions. I mean, things that seemed in the early 20th century, small little niggling things that didn't fit in quite into the prevailing understanding led to then, I mean, they seem like small things, some graph of radiation not quite matching at some end, and something about some measuring the speed of the ether, not really matching. Some people dismiss them, but then they led to something new. So we should remain alert. Anyway, so thanks very much, everyone, and thank you, David, for very patiently taking us through. It's a small memento mug from ICTS. So thanks again, and we'll meet outside. There is chat, and as we say, high tea, so please join. As we say in ICTS, let's chat over chat.